I want to test my radar up to what range of noise that the radar will withstand. And coming to the types of radar, there are two types of radar. One is surface radar and the other one is volume radar, volume clutter and surface clutter. Coming to the surface clutter, that includes the sea, terrain, man-made structures, and in the volume clutter, it includes birds, trees and rain, etc. The clutter will be modeled in different PDFs. PDF is nothing but a probability density function, and that distribution depends upon the nature of the clutter. I am having, if I am considering a sea, surface of sea, the probability density function is someone, and if I am considering a land clutter, the probability density function will be other one. The types of distributions are Rayleigh distribution, log normal distribution, and variable distribution. In my project, I am discussing about log normal distribution. Why? Because I am mainly concentrating on sea clutter. Objective of my project is to generate a clutter which is obtaining at sea levels. Coming to the block diagram, this block diagram will be explained in the few next steps. These are the implementation methods. I am dividing my project into 4 modules. In the first module, I am generating pseudo-random numbers. Why? Because the noise will not be a continuous one. That will be a random one. For that purpose, I am generating pseudo-random numbers. In the second stage, by using that pseudo-random numbers, I am generating Gaussian noise. Why? Because in the nature, we are getting so many noises that will be in the form of Gaussian only. In the third phase, I am designing a matched filter to get the frequency output. And in the final stage, I am testing that output, that matched filter output on the radar prototype. Coming to the first stage, the implementation of random numbers. There are 2 types of random numbers. One is true random number, another one is pseudo random numbers. True random numbers means here I will not get any repetition in the numbers. Coming to pseudo random numbers, if I am taking n-bit pseudo random numbers, the numbers will be repeated after 2 power of n iterations. The implementation methods of these pseudo random numbers is a blob shape generator, is a chipper, and here I am using this method, linear feedback shift register, LFSR technique, for generation of pseudo random numbers. This is the block diagram of the LFSR, linear feedback shift register. This is the example of 4-bit random number generation. If I am taking a 4-bit random number generation, the XOR operation will be done between third and fourth of 4 numbers. These are the XOR tap points for different generation of different bits of random numbers. In my project, I am generating 32-bit random numbers. Means I am doing XOR shift on between 1, 12, 22 and 32 bits. This is a snapshot of implementation of my random number generation project, and this is the FPGA design flow. How I am implementing my project on the FPGA. FPGA is nothing but field programmable gate array. After writing my code, I am synthesizing my code on Xilinx software. After the generation of my .bit file, I am downloading it into FPGA using JTAG. After the generation of .cdc. .cdc is nothing but chip scope definition file that I am verifying my output on the chip scope, and here I am getting the output like this. These are the generated random numbers. In the second phase, I am generating pseudo random numbers using this. I am generating Gaussian noise using these pseudo random numbers. This is the second phase. For generating these pseudo random numbers, manipulating 32-bit random numbers is a very difficult part. For this, I am dividing these 32-bit random numbers into 2 parallel 16-bit random numbers. By using that 16-bit random numbers, I am generating a Gaussian sequence using this technique. This is a mixed convolutional technique. This is the formula for mixed convolutional technique. Here A is nothing but the multiplier constant, and Xi is what is the sequence I am taking, and C is the incremental constant. M is the modulus for the overall thing. And for dividing 2 16-bit random numbers, I am using, this is the box mirror technique for dividing 2 32-bit random numbers into 2 16-bit random numbers. And this is the overall block diagram for my Gaussian sequence generation. for Gaussian sequence generation in LabVIEW. And this is the output for my Gaussian sequence generation. From this Gaussian sequence, for 116-bit Gaussian sequence is undergone to some techniques to give temporal characteristics, and 116-bit is maintained constant for my output. And this 16-bit Gaussian sequence is gone to FFT. This 16-bit is gone to FFT, undergone to FFT, and this output of this FFT is multiplied with the radar multiplied output, filtered output. I will show you the output. Let us consider this is the output of a radar. It is containing both the targeted output and the clutter noise also. And what I am doing is I am filtering this output with a Kaiser filter or some filter, whatever I want. And after that filtering, I am getting this sequence. This is multiplied with the 16-bit Gaussian sequence, and the output will be like this. This is the time domain analysis, time domain output, and this is the frequency domain output. After that, what I am doing is I want to do.
And if you apply random here?
No, actually random number is the first thing, basic thing for generating all this. Here I am getting time domain, frequency domain, and to convert this frequency domain into time domain, I am doing inverse fast Fourier transform here. After doing inverse fast Fourier transform, 116-bit is kept constant, right? This 16-bit is undergone to ZMNL technique. That is nothing but zero memory nonlinearity technique. That technique is used for converting Gaussian into non-Gaussian. That is my required output. The output is like this.
So your goal is to convert basically, map it to.
I want to generate a clutter. So clutter is nothing but unwanted radar return, means noise in the radar. Why? Because if I design a radar, if I want to design a radar, I want to know up to what range or up to what noise level that radar will withstand. For that purpose, I am designing this project, sir. After testing on the radar prototype, this is my overall output that I got on the radar. These are all the tools that I have used. A MATLAB tool for generating random numbers and designing a filter, and Xilinx for random number generation, and LabVIEW is for overall block diagram. And I have implemented my random number generation on Vertex 5 FPGA, and the snapshot is this. This is the hardware that I have used. And the application is, I am using this app. As you know that Navi people are using this one. The project that I have done in RCA are using, Navi people are using this project. And for range and velocity simulation in C using ships. My conclusion is
already implemented in Navi?
Yes, sir. They are using from 4 months.
Oh.
Yes. I have generated a C clutter by using FPGA. How can I say that that is a log normal one? Means if I take the power samples from these different parts, I will get this, and I implemented this on MATLAB. I will get output like this. This is the probability density function of log normal distribution. And these are my references, and these are the papers that I have published earlier.
Oh, okay. In connection with this?
No, in connection with this project. And this is for first one, random number generation, and this is for Gaussian mass generation. And all over my project was implemented.
You are a faculty or student?
Now I am working as faculty and a research scholar from my campus. If you have any questions.
Any questions?